To the last phase, I want us to look at reflection. Kevin,
Yeah, yes, sir.
please. So for reflection, we have reflection in the x-axis, reflection in the y-axis, reflection in the line x equals a, y equals a, y equals x, y equals x. These are the major types that we look at. So we don't have enough time. Let me summarize it. So for reflection, it's very simple. Reflection is a flip. Okay. If you flip something, you are reflecting. So you watch our exercise books. If you are turning the pages, you are flipping. Okay. Or your textbooks, if you are turning the pages, you are flipping. So once you are flipping, then that is a reflection. Now, the flip and the turns look similar, but the major difference between flip and turn is that whilst you are turning, you turn about a fixed point. Whilst you are flipping, you flip about a line. So you realize that if you are turning the pages of our books, you are flipping. Why? Because your turns are about a line. The spine of the book is what makes your flipping possible, right? So flips are about lines, while turns are about fixed points. So if you are reflecting, you are flipping. And if you are flipping, what happens is that the major concept here is that the distance, the perpendicular distance between your point and the axis you are reflecting on is the same as between the axis you are reflecting on and the image. So that is the key difference. I know you've done reflection in the x-axis, and you know that reflection in the x-axis, what happens is that if this is your x-axis, x and y-axis, this is the point. The image comes behind the x-axis. This is the point. The image comes behind the x-axis. Realize that the y here is positive. If it's coming down, the y is negative. So for reflection, always x is the same, whilst y becomes negative. And if you come to the y-axis, it's the reverse. So if you know the x, the reverse is that down the negative will come to the x while the y is the same. That's reflection in the y-axis. So if you know the x-axis formula, you coming to know the y-axis is very simple. You just send a negative to the x. For reflection, don't forget, it's not about rotation. So x and y would not interchange positions. They will still be at where they are. It's just that y will become negative at a point, and then the other one, x will become negative. If you are reflecting in a line x equals a, for x equals a, there are several lines on the x-axis. If you watch, we can have one, we can have two, we can have three, we can have four. All of these, you can have neck one, you can have neck two. All of these are lines on the x-axis. This is x equals one, x equals two, x equals three, x equals four, x equals neck one, x equals neck two. And the y-axis is also called x equals zero. So the other name for reflection in the y-axis is x equals zero, while the x-axis is y equals zero. So if you are reflecting on any line on the x-axis, x equals 3, x equals 4, x equals 2, x equals 1, those black lines are drawn. If you are reflecting on any of those lines, we say you are reflecting on x equals a. So if you are doing x equals a, there's a formula for it. The formula is such that you have 2a minus x, then you have the y. where the A is the line you're reflecting on. So if you're reflecting on x equals 3, it means that your A is 3. So in the formula, where you see A, that becomes 3. 2 times 3 is 6 minus x. So if I'm reflecting on the line x equals -2, it means that A is -2. So this becomes 2 times -2, -4 minus x. That is how it is. So this is just a general formula. When you do the line on which you are reflecting, then you get the specific formula that you can use to do your reflection. If you are doing on y equals A, it's still the same thing, xy, just that whatever you have up will come down. So x will still be the same. Then we'll have 2A minus y. And if I'm reflecting the line y equals x, this is also simple. It means that the y is equal to x. So anywhere I see y, the y is becoming x. And the x is the same as y. If y is x, x is y. So anywhere I see x, x is becoming what? Y. So that formula is xy becomes yx. By reflecting the line y equals x. If I reflecting the line y equals negative x, so with y equals negative x, it means that the y part is negative x. So if the y part is negative x, then the x is what? Can divide through by -1. Then this goes off. So the x becomes what? Negative don't stay down, you bring it up, -1. So the x is -1. So if I'm reflecting in the line y equals negative x, that one also becomes -y, -x. So let's take some examples to demonstrate this. So let's say I have a point A, 5, 6, I have point B, -3, -5. Okay. And I'm reflecting this. Reflecting A and B, let's say 1 in the line y equals -2, then 2 in the line x equals 3. Let me take the first one. I'm reflecting in the line y equals -2. Sometimes to remember, they can call this line y plus 2 equals 0. It's the same thing. If plus 2 crosses the equal sign, negative, right? Okay, so we go y equals -2. So you know that formula, I said xy becomes 2a minus y and then x. So now my a is -2. So my xy should become x, then 2 times -2 is -4 minus y. So if I have this, this is now the specific formula I'm going to use to reflect A and then B. If I'm reflecting A, the x part of A is 5 and the y is 6. So if I have xy, so the x part is 5. So -4 minus y, and the y part is 6. So my image becomes what? 5, -10. If I'm reflecting -3, -5, it means my x part is -3 and my y is -5. So that's -4 minus -5. So that becomes -3, then -4 plus 5, and that is what? 1. And these are the images that I'm going to plot. If you are doing it graphically, then you plot that on the graph. Is that okay? So if you are now reflecting this in the line x equals 3, A 5, 6, B -3, -5, x equals 3. So that to quote the general formula, xy is becoming 2a minus x, then y. So xy should become 2, A is 3, right? Times 3 minus x, y, which is 6 minus x, y. So now if I take my A, 5, 6, it means that my x is 5, so 6 minus 5, my y is still 6. And that should be 1, 6. If I take the B, my x is -3, so 6 minus -3, and my y is -5. So that becomes 6 plus 3, and that is 9, -5. And that will be the image. So if you are also asked to, let's say, reflect 3, 2 in a line y equals x. So y equals x, xy should be what? Yx. That's all about it. So if I have 3, 2, and I'm reflecting the line y equals x, the 2 starts and 3 ends. As simple as that. But if I'm reflecting the line y equals x, y equals x becomes y, x. I'm rushing it because of the time. So 3, 2 should be negative of the y. So that's negative, -2, and that's 2. And then -3. So our answer is 2, -3. And that ends it. Are we okay?
Please let's proceed.
So that is it for reflection. For translation, that is the easiest. For translation, you always have something we call a translation vector. So if you are translating a point xy, you only have to add the translation vector to the point. And that gives you the image. So we say point plus translation vector will always give you image. Translation is also called a slide. And so when someone scores a goal in a football match, and that person slides on the field, what the person is doing is translation, slide. When you slide, it's translation. So we watch the X and we watch the Y, and we watch the distance along the X that you slided, and the distance along the Y that you slided, and that gives us the translation vector. Right? So now, I saw a question. So this is it's very simple. Add the translation vector to the point and you have the image. I saw a question somewhere. Why they drew a graph? And students couldn't answer that question. Let me just make a sketch of the graph here. Okay. Let's do this. Let's say this is P. And this is Q. Okay. Then the question was, what is the translation vector if P was translated by the vector and Q is the image? What is the translation vector? And that was the question. And because we are only used to the formula, we don't know what to do in this situation because these points have not been named. Okay, so it's very simple. If you want to know the translation vector here, it's all about movement. You know, on the x, if you move left, it's negative. If you move downwards on the y, it is negative. If you move upwards, it is positive. If you move towards the right, it is also positive. So with this, what we do is that we know that this point here is the same thing here. And the point at the tip here is the same thing here. Here. It's here, sorry. It's here. And this, sorry. And this one here, the image, this one, the point here, is also the same as the one here. So I would have to make movement from the green to the green, the blue to the blue, and the other one to the other one. So I'm making the movement, you see, this is along the x, along the y. So I can make the x first. So in making the x first, 1, 2, 3. Then I come, it's on it, so I come downwards. 1, 2, 3, 4. So it is 4 downwards. And then 3 towards the left. And left is always negative. Downwards is always negative for the y. So this one, I moved neck 3 and then neck 4. The same translation vector should affect all the others. So you try that to see. So let's try this one too. And see how it works. 1, 2. It's here, so 3. And I come downwards. 1, 2, 3, 4. Left downwards. So that also neck 3, neck 4. Then let's do the other one to the blue one too and see how it goes. The other one, 1, 2, 3, left, and downwards, 1, 2, 3, 4. So it's still also neck 3, neck 4. So the translation vector is neck 3, neck 4 because it's the same across board. So this is how to get translation on the graph. So if they give you a translation vector and you have a point drawn, you can decide to just make movement on the graph. If it's 3, 4, you just go right 3, upwards 4. Wherever it is the image. And in that case, you don't do any calculation. That's why on a graph like this, we don't mark for calculations. All we mark for is the images. So you can do it on the graph without doing any calculation. It's very simple. Just make movements. And that ends it. And you get a full mark for that. So this is briefly rigid motion and transformation graph. This is all it is. Any question?